Lecture 15 covers section 5.4. At the end of today's lecture, you should be able to understand static and kinetic frictional forces. Now, a frictional force is a force that acts to oppose the tendency of our contacting surfaces to move relative to one another. In this course, we're going to study dry, or Coulombic, frictional forces. Now, fluid forces is going to be the focus of fluid mechanics. To begin, let's consider a crate with a weight W sitting on a surface. The weight of the crate acts at the center of mass. Now, there has to be a normal force to oppose the weight of this crate. So N would be existing in our positive direction. Now, say we have an applied force, P, acting on this crate. What would have to exist for this crate to be in equilibrium is a frictional force, F sub F. This frictional force is going to counteract P, such that our body does not move. As we begin to increase P, our frictional force must also increase. We can see this on our frictional force versus P graph. As we increase P, our frictional force is going to increase, and the slope of this line is going to be unity. Now, our frictional force does not increase indefinitely, but it's going to increase to some limit, and this limit is denoted as our maximum frictional force. If we do not exceed F sub max, we can say that our frictional force is solely dependent upon our normal force and our coefficient of static friction, mu sub s. That is, our frictional force is equal to mu sub s times n. Now, when we reach our maximum frictional force, we are going to exist at a state called the condition of impending motion. Any further increase of P is going to result into motion of our body. Now, once our body is moving, our frictional force is going to decrease, and this is due to the decrease of our coefficient of friction. Our new coefficient is known as our coefficient of kinetic friction, denoted as mu sub k, and our frictional force is then expressed as mu sub k times n. Mu sub k is always going to be less than mu sub s. That is, once our body is moving, it is easier to keep it moving. Now, say our applied force P has a y component. This is shown in panel A. When we have a y component, we are going to increase our normal force, but we also have a frictional force that is going to counteract our x component of our applied force P. Now, what we can do is combine our frictional force and our normal force into a resultant denoted as R. And R is going to act some angle phi from the line of action of our weight. This is shown in panel B. That is, if we take the summation of forces in the x direction, in panel A, we'd have P sub x would be equal to F sub F. In panel B, this would be R sine phi is equal to P sub x. If we take the summation of forces in our y direction, in panel A, we'd have our normal force being equal to our weight plus P sub y. And in our right panel, we'd have R cosine phi is equal to W plus P sub y. As P sub x increases, so does R sine phi, i.e. our frictional force has to increase. That is, as our applied load P has less of a y component, our frictional force is going to have to increase to counteract this applied load. That is, as phi continues to increase, our system will reach the condition of impending motion. That is, F sub F will approach F max. And at this angle, we call phi the angle of static friction, denoted as phi sub s. Now, if we recall, R sub y is equal to our normal force, and R sub x is equal to our frictional force, we can say the tangent of phi sub s is equal to our maximum frictional force per our normal force, which is equal to mu sub s times normal force per our normal force, which is equal to mu sub s. And for small angles, i.e. when phi is less than 10 degrees, we can say phi sub s is approximately equal to mu sub s. Once phi sub s is exceeded, that is, once we have motion, the magnitude of our frictional force is going to decrease, which means our angle phi decreases to phi sub k, and this is denoted as the angle of kinetic friction. Thus, we can say the tan of phi sub k is going to be equal to our frictional force per n, which is equal to mu sub k times n per n, which is equal to mu sub k. For small angles, phi sub k is approximately equal to mu sub k.